Yes, class. Good evening. So yesterday we had completed till this part, your Faraday's laws of EMF. So E is equal to minus d phi over dt. Faraday's law says what? What was the statement of Faraday's law? Yes, Astha. What was the statement of Faraday's law? Anushka, can you answer? Faraday's law.
Uh, yes, ma'am.
Ma'am, did you ask me?
Yes, yes, Astha. I was asking what are the laws of Faraday's law. Yesterday we did no. So what was the statement of Faraday's law?
Whenever the magnetic flux linked with the coil changes, the EMF induced is directly proportional to the rate of change of magnetic flux.
Yes, good. So two statements of Faraday's law were there. Firstly, whenever there's a change in magnetic flux gets changed whenever there is an increase or decrease in the magnetic field. So what happens? As the magnetic flux gets changed, induced EMF is there in the circuit. EMF is induced in the circuit, whose magnitude is directly proportional to the rate of change of flux. And negative sign we'll be discussing today, that is Lenz law. So modified forms we had seen in terms of charge and current. Till the time other students are also coming, try this question, then we'll discuss it. It's a very direct question. Two questions are left. Let's do it before we start with Lenz law. Yesterday I have sent you your scores as well. Most of you have done well. Those who are getting below 15, just work on your numericals. See class, nobody has answered till now. Let's discuss it. A 10 ohm resistance is 10 ohm, has 1000 turns. So number of turns in that coil is 1000, and at a time 5.5 into 10 to the power minus 4 of flux passes through it. Okay, this much webers of flux have passed. So this is the initial flux. Initial flux is 5.5 into 10 to the power minus 4 webers. Final, if flux falls to how much amount is the amount by which the flux is falling? Flux has reached 0.5 into 10 to the power minus 4, and time is 0.1 seconds. So you have to tell the EMF that is generated as well as the charge. So it's a formula based question directly. See, the change in EMF, the change in the magnetic flux will be what? Change in the flux will be 5 final minus 5 initial. 5 final is 0.5. 5 final is 0.5 into 10 to the power minus 4 minus 5.5 into 10 to the power minus 4. So this gives minus 5 into 10 to the power minus 4. This is the change in flux. So what's the change in time? Time is 0.1. So yesterday we had seen a formula which said EMF is minus d phi over dt, or we can also even write it as delta phi over delta t. So minus, what is flux over here? Minus 5 into 10 to the power minus 4 divided by time, that is 10 to the power minus 1. So this gives you positive 1, and this becomes 10 to the power minus 3 volt. This is the EMF that you will obtain. So you just have to find out the change in flux and put it in this formula. Then charge flowing. See, this relation we had seen. If you have to find out the charge, take the change in flux divided by the resistance. Whatever is the change in flux divided by the resistance. And here resistance value is given. One more thing before we do this. See, this we have calculated for a single turn. If there are 1000 turns, if this is for a single turn, for 1000 turns, it will be 5 into 10 to the power minus 3 into 10 to the power 3. This gives you 5 volts. Now, dq is equal to d phi over dt, or you can simply say change in phi over change in time. So this gives you minus 5 into 10 to the power minus 4, not time, resistance. Here it is resistance. This, otherwise this becomes the value of EMF. Resistance. So resistance is how much? 10, I think. Yes, 10 ohm is the resistance that is given. So this divided by 10, this is equal to minus 5 into 10 to the power. This becomes minus 1, so minus 5 coulomb, like this. So change in flux, EMF's main formula is this. See, every formula is based upon this. One more question we'll do. First note it down, then we'll discuss that. One more question before beginning with Lenz law. Mariam and Imad, both of you were absent yesterday, no?
Yes, ma'am.
Mariam, try to be a little regular. I think it was a maths first class that was missed, but Mariam, your attendance is irregular. So just try to attend all the classes.
Ma'am, done.
Done. All of you?
Yes, ma'am.
All right. Let's just do one more question. This is much similar to AC diagram. We had done it in the first class, no? So do one thing. First, note down the question, then I'll start. Just note this down.
Ma'am,
Yes. Yes, Liana.
ma'am, for the previous question, while finding the charge, why won't we consider the number of turns as well? Because it'll be like total flux, right?
Yes, yes. See, no, total number of turns can also be considered. This charge will be for a single turn. It was given charge flown through the coil is written. So yes, you're right. We have to multiply it here as well with the number of turns, because otherwise this will be for a single turn. But we have to find the charge throughout the coil. So yes, right. Thank you. Just make this correction out of it. The way we have multiplied this, no, for 1,000 turns, it will become 10 to the power 3 here as well. So your answer will become minus 5 into 10 to the power minus 2. Please make this correction. Thank you, Rihanna. Just make this correction out of it. Number of turns will also be multiplied. Both these parts are just similar to each other. Just note it down, read the question, then I'll answer this. Have you all written the question at least?
Yes, ma'am.
All
That's
right.
in note 2.
Okay. Just note it down. See here in this question, the question says what? Coil is there, cross-sectional area is in. Magnetic field B is kept perpendicular to the field. Fine. Plane is perpendicular to the field. Now in this position, remember the way we had started the questions of AC dynamo? The plane of the coil was perpendicular to magnetic field. Similarly here as well. Now in this position, normal to the coil makes an angle of 0 degree with the field. This is the required angle. This is the angle theta, no, that we consider. Angle that the normal to the coil, that is the area vector. Normal to the coil. This means what? The area vector. So area vector makes with the field, magnetic field. This is what the angle we desire whenever we write the formula of magnetic flux. When we write no BA cos theta, that theta is this angle only. Then it says coil rotates at a uniform rate to complete one rotation. Means coil has started from this position, then coil has rotated, then coil has again rotated, and initial this position has reached back, and once it rotates again, this position is reached back. The way we did no coil AC dynamo we were doing. Coil is placed, it's like you imagine your palm is facing first towards the right side. Shift your palm. Palm is now facing outwards. Shift your palm. Now your palm is facing towards the left. Then your palm is facing towards you. Then your palm is facing again back towards the left. So this is one rotation of your palm. Just instead of this, imagine a coil is here. So this entire duration is T. Fine. T is the total time that is taken to cover all the 4 positions. Now it is asking us to calculate average induced EMF in the coil during the interval when the coil rotates from 0 degree to 90 degree. See class, this can be understood in this. This is the initial point, 0 degree. Coil rotates in such a manner. First, the view that you will observe is this. Then the view that you will be able to observe is this view. This is at 90 degree. Then the coil again rotates, now pointing towards this. That makes it 180 degree. Then it again rotates when the coil is facing towards you, that is 270 degree. And again it will complete here 0 degree, or you can simply say 360 degree. 0 degree or 360 degree. And the entire time taken in this journey from 0 degree to reach back 360 degree, this is capital T. Now tell me class one thing. All of you reply me in the chat box. All of you should try this. If the coil is moving from 0 to 90, from 0 to 90 degree, this part, then what will be the time period that I should consider? Quickly reply me in the chat box. Time period, total time period is T. If only from 0 degree to 90 degree, what should be the time period? Yes, both of you are right. Astha and Anushka. Others also, see, so simple. Total time taken from 0 to this back quadrant 3 is capital T. If only this time period I'm asking you, what will it be? Yes, Imad. Perfect. Right answer. See all of you, this time period will become T by 4. T by 4 from 0 to 90 degree. Now your flux is what? Flux is BA cos theta. So from 0 degree, so initial flux will be BA cos 0. That gives BA only. And final flux is phi 2. This is what? BA cos 90 degree. Final position is 90, so this becomes 0. So change in flux is what? 0 minus BA, that gives BA. Time period is not given to us, whole time period is given. So we have calculated the time period that is required to us. So minus delta phi over the total change in time, or total time you can say. So minus, this is what? This is minus BA. This is minus BA from here, divided by T by 4. So that becomes 4BA divided by T. This much is your answer. Vote this much for us. Got it? Are you all able to understand this?
Yes, ma'am.
All right. So do one thing. This part I have done. At least send me the answers of 90 degree to 180 degree.
Ma'am,
Yes. Yes, Himatsu.
so is it possible to get the same answer again? Or
Is it possible?
to get the same answer for again for 90 degree to 180 degree purposes?
90 degree to 180 degree. Yes, from 90 degree to 180 degree, the coil can rotate.
But ma'am, it will also be like T by 4 only. No? Even that area is T by 4.
Exactly. So it will be T by 4 only. Yes. See, any question can be given to you. In your NCRT, no, in your previous year question, this question was there with a slight modification, I think. Random time can be given to you. If it's from starting point is 90 degree, it means the coil is in this position. Then the coil rotates, where you can see the coil from through this angle like this, and the coil has stopped. So again, now we are just focusing on this part. This will also be T by 4. Now, if the question is a little modified, it can be asked, if the coil rotates from 0 to 180 degree, what will be the time that you all will take from 0 to 180?
By 2.
T by 2. Perfect. And who all are present? Yes, Ryan. If it's from 180 degree to 270 degree, how much time duration will you take? From 180 to 270. Ryan?
Yes, ma'am.
How much will it be from 180 degree to 270 degree? If we are referring to this. See, it will again be T by 4. This is a complete, it's like complete time is there. This is time period T. You have divided the time period into 4 parts, and any of these parts are mentioned, select that area. For example, 0 to 270 degree. This is 0, this is 270 degree. So this entire, this is what? T by 3. 3 parts out of the total parts that is available. So this is time period is, it will become T by 3. Like this you have to choose. So any modification can be given, 90 degree to 270 degree 270 degree to 360 degree, from 0 to 270, 0 to 180, 180 to 360. Anything can be given. EMF, the formula of EMF will be minus d phi over dt only. So second part says what? Second part asks from 90 degree to 180 degree. So same thing. See, for the second part, phi initial means from 90 degrees. So that becomes BA cos 90, which is 0. Phi 2 becomes to 180 degree. So this becomes minus BA. Their change will also become minus BA. Again, you will get the same answer. Minus delta phi over delta t. This is minus BA over the time period, that is t by 4, and this will become 4BA divided by t. Same thing, same answer. Because since it is 180 degree and it has made it again minus. Otherwise, had it been a different number, 0 degree or something, then we would have got a negative sign of it. Okay, quickly note it down.
Ma'am, I'll just be back in a minute.
Okay. Done? Have you all written till here?
Yes, ma'am.
See, Lenz law, let's do. From Lenz law, only theoretical questions you will get. Only theory questions. And you have new questions on Lenz law. Maximum time from EMI, no, from this portion, induced EMF. Lenz law is somehow added in the question. For example, your question will comprise of 3 parts. First part will ask you to calculate the magnitude of EMF. Second part to calculate induced current. Third part will say predict Lenz law in this, or it will write the statement of Lenz law, or separately also it can be asked. Fine. So Lenz law is a separate topic. Separately also it can come, and it can come combined also, because our total Lenz law depends upon that. Now see what is meant by this Lenz law. First understand, whenever there was a increment or decrement in the magnetic field, there we had what? There was a change of flux, magnetic flux. Yes, this is all clear to all of you. Magnetic flux is increasing, flux increases. Magnetic flux decreases, flux decreases. Because of this magnetic flux, what happens? There is production of induced EMF and production of induced current. So current will have a certain direction in the coil, whether clockwise, anti-clockwise, through the wire, whatever directions we have already covered in magnetics. So there will be a certain direction of induced current. Now, induced current does what? It arranges its direction in such a manner that it has to oppose its cause. Now, what was the cause of induced current? Induced current's cause was change in flux. This was the cause of induced current. So the direction of induced current will be in such a manner to oppose this. If flux is increasing, let's take the example, flux is increasing. Induced current will set its direction in such a manner that total flux decreases. If flux is increasing, it will arrange itself in which manner? So that flux decreases. And if flux is decreasing, then it will arrange it itself in such a manner. The direction will be such that the flux will decrease automatically. Right? This is known as Lenz law. Whenever the current opposes its cause, you have to remember, cause is what? Cause is simply your change in magnetic flux. So if magnetic flux increasing, magnetic flux decreasing, that becomes the cause of induced current. Now induced current will oppose its cause, the cause that is being produced by it. It will oppose its cause. Now whatever direction will be there of current, that all the directions you have studied, that is seen. So magnetic flux increases, decreases, induced current is present, its direction in such a manner that it opposes its cause, and the cause of it is magnetic flux. So magnetic flux gets opposed. The statements are also written. Direction of induced current is such that it opposes the cause that produces it. And what produces it? The change in flux. And it's in conservation of energy. There are many things like conservation of mass, conservation of charge. So this is in conservation of energy. Actually, reason is that the total work done gets remain same here, gets consumed, whatever is the total work done. Now you can understand this through this example. Before that, remember when we were doing magnetic dipole, we did the polarity of the coils. If it was south pole, then I had asked you to make arrows at the south pole. These moving arrows will give you direction of south polarity. North polarity, make arrow, right N, put the arrows like this. This gives you direction. So you don't even need to remember. So south polarity is clockwise, north polarity is anti-clockwise. Otherwise, you will be able to not remember it. So it's better if you remember it this way. Just a second, just a second. See, remember these polarities, what we were discussing? Yes. So if it's south polarity, make it like this. So that you will remember it is clockwise and this becomes anti-clockwise. Now let's see the example. There's a coil, circular coil is present. And I am bringing a bar magnet with north-south polarity, and this bar magnet is coming towards it. Now there will be magnetic field. So what's the cause? Cause is approaching north pole. Approaching north. Now, direction of current in the coil has to be in such a manner that it opposes it. Now, opposes the cause. Cause is approaching north pole. It means we have to somewhat throw the magnet away from the coil. Direction will be what? If the north pole is coming, then the aim is to repel the north pole. And how can you repel the north polarity? By developing what kind of polarity? Which polarity will repel north polarity?
Ma'am, no.
North pole, exactly, because that becomes like poles. So it means this coil will develop north polarity. So direction of induced current will be what? Anti-clockwise will be the direction. And then this north polarity will repel this. So by this way, it has opposed the cause that it was producing it. Understood? For example, take one more example. South, north. Bar magnet is coming with south polarity. Now the cause is what? Cause is south polarity's approachment. And now aim becomes what? Aim becomes to repel south polarity. So aim is to now repel south pole. So only if you develop south polarity, then only it will get repelled. Now it will move back. It won't be able to do its purpose. South polarity came. Magnetic field lines were increasing, but as soon as it developed, the coil developed south polarity, it opposed the cause. So direction of induced current will become clockwise. So any question like this comes, you have to mention the direction. This is Lenz law. Direction of induced current is in such a manner that it opposes the cause that it is producing it. Or let's take one more example. This is a bar magnet, north-south. Bar magnet is moving away. Now the cause of the current is what? Magnetic bar magnet is moving away. It means magnetic field lines are decreasing, number of field lines are decreasing. So there's a change in flux. Flux is decreasing or increasing? Decreasing mainly here. So this change in flux is what? This change in flux is now the cause. So this is now receding, or you can simply say the north pole. Moving north pole is the cause. Moving away of north pole is the cause. If the north pole is moving away, now the aim will become to attract north pole. Now this will become the aim. So if it develops south polarity, then only it will be able to attract north pole and it will oppose it. So direction will become again clockwise, direction of induced current. Like this you have to remember. One more. This is south polarity, this is north polarity. South polarity is moving away. Now aim is what? This moving away of the south polarity is now our aim. So is now the cause. Now we have the induced current's direction is in such a manner to oppose the work that is being done over here. So if south pole is moving away, induced current will try to attract it. Only north pole can attract south pole. So direction will be anti-clockwise. Got it? Like this, you have to apply Lenz law. And this is the meaning of Lenz law. One more thing, one more big case. Let's do this. See. There's a coil that I have taken over here. Now this coil is doing what? Let's say this coil is coming inside. So now tell me, if this coil is coming inside, so definitely number of field lines will increase. Why? Because this coil will now enclose itself. As it will move downwards, as it will move closer, the number of field lines that will be present will increase inside this. So if field lines will increase, what will happen to the magnetic flux? Here magnetic field increases, so the flux also increases. If flux is increasing, do you understand this? This is the first coil. Coil 1 is moving into this. Magnetic field lines will become more. So magnetic flux will also become more. If magnetic flux is becoming more, there's a change in the flux. Obviously, there will be an induced current. Now, there will be an induced current that we all agree with this. Now, the direction of induced current will be in such manner that it has to oppose the cause. It means if flux was increasing, induced current has to set its direction in such a manner that the flux decreases. So how can the flux decreases? If to decrease the flux, we have to decrease the magnetic field. See, all these magnetic fields are producing, these original magnetic fields are pointing inside. So if original magnetic field lines, understand this carefully, if original magnetic field lines are pointing inside into the page, if somehow the induced magnetic field is produced outwards, then the net magnetic field will be the subtraction difference of these, right? If two vectors are in exactly opposite direction, what do? We subtract the vectors. So it means now the magnetic field will decrease. If the magnetic field has to increase, original magnetic field is pointing inwards and the induced magnetic field also point inwards. So net magnetic field of the system will become what? Induced plus original. That means increment in the magnetic field. These 2 points, do you understand separately? Not from this. How to, if two vectors are exactly making 180 degree to each other, if this is pointing outward, inwards, this is pointing outwards, net magnetic field will be low. If both the vectors are pointing either outwards or inwards together, but in the same direction, that will result in the addition of the quantities. First, tell me, these 2 points you have understood? How the magnetic field increases, decreases?
Yes, ma'am.
Yes, ma'am.
Okay, now see, here is what happening. Magnetic field is increasing, flux is increasing. So magnetic field's direction has to be set in which manner? Where the flux decreases. For flux to decrease, we have to choose where magnetic field decreases. It means if original magnetic field is pointing inwards, the induced magnetic field should point outwards. Understood? Your magnetic field should point outwards now, the induced magnetic field's direction. So now do one thing. Keep your thumb outwards on the screen and see the curvature of fingers. Everybody do it along. Keep your thumb in the direction of this induced current, which we want. Induced magnetic field. Induced magnetic field we have chosen, it will be outwards. Then only there will be a subtraction in both the magnetic fields and magnetic field will get decreased. So if you point the thumb towards yourself, right hand, what is the curvature of fingers?
Anti-clockwise.
Anti-clockwise. Perfect. So direction of magnetic field induced current will be anti-clockwise and direction of induced magnetic field will be outwards. Why did we choose the magnetic field outwards? The reason is that now both the net magnetic field will be lesser because induced magnetic field will get subtracted from the original magnetic field that is present. So a decrement in the result will be there. Magnetic flux will decrease and the purpose is solved. Lenz law is applied. Now see one more thing. The coil, this coil is now moving away. This is the second coil. This coil is now moving away. So yes, Imad, can you tell me, will the magnetic flux increase or decrease?
I think so. It
It will?
increase.
Why will it increase? It's moving away from the magnetic field region. So it will decrease. Okay, because see here it was what was happening, this was entering, so lots of magnetic field lines were getting enclosed through this area, so it increased. Now it is leaving. As soon as it will keep on leaving, number of field lines will get decreased. So first thing, magnetic field decreases and flux decreases. Fine. Now Liana, tell me one thing, what will be the aim of induced current? Liana.
Ma'am, can you repeat?
Now what will be the aim, direction of induced current? It will try to do what?
It will try to pull it back in.
No, not pull it back in, just think in terms of flux. If flux is decreasing, induced current will try to, here flux is decreasing. So aim of induced current now will become what? To decrease the magnetic flux more. Yes, Liana? what will be the purpose of induced current? Now it will try to align itself in a direction which will try to do what? Increase flux or decrease flux?
Decrease flux.
No, see, flux is already decreasing. Lenz law says that it opposes the cause. So it will try to increase it. Yes, Razan, it will try to increase it. See, what did we study? Induced current direction is in such a manner that it opposes the cause. So if magnetic flux is decreasing and induced current will also decrease it, then such a huge decrement will not oppose it. It will only support it. We have to oppose it. So aim will now to increase the flux. Aim will now be to increase the flux because flux is decreasing. Coil is moving away, flux is decreasing. Aim will be to increase the flux. Yes, Mariam, tell me one thing. If flux has to increase, direction of induced magnetic field will should point where? Outwards or inwards? This is original. Mariam, just try once. Rayan, can you answer? Rayan? Okay, Mariam has answered outwards. No, Mariam. See, you people have not understood, I think, the first part properly. Everybody is answering exactly in the opposite manner. If flux is decreasing, our purpose is to now increase the flux. So you have to have the induced magnetic field's direction exactly in the way where, just a second. Plus do one thing. There's an issue in the laptop. I'll fix it. Just note it from here. Then I'll discuss that. Yes, class. You can continue. Let's just discuss that small part that was left from Lenz law. Because this here you people are making a lot of mistakes. See class, I'm repeating this again. This is very important part. Questions are just based on this from Lenz law, and Lenz law is a very important topic from your board's point specifically. See, this coil is there. This coil is exiting. If it is exiting, if it is coming out of the magnetic field region, it means number of magnetic field lines are decreasing. So flux will also decrease. First point. First tell me, is this clear? Why will the flux decrease and magnetic field will decrease?
Yes,
Ma'am,
ma'am.
just one.
Imad, are you asking something?
Yes, sir. I just kind of explain it again.
Okay. See, this coil is moving away. Now, initially the coil must be somewhere here. All the magnetic field lines are within this. Now what is happening? The coil has now sliding outwards. So it might have, now it has reached this point. Now as it is going away, there will be a point where only this part will be enclosed. So this is air part. Magnetic field lines are till this region only. What is happening? Initially magnetic field was confined. All the magnetic field lines were there. Now as it is moving away, as it is receding away, number of magnetic field lines that were present within the area are decreasing. Yes?
Yes, sir.
If magnetic field decreases, flux automatically decreases. Now see, if flux is decreasing, induced current's direction will be in such a way to increase the flux. Why to increase the flux? Because it has to oppose it. In the first part, flux was increasing. So induced current wanted to decrease the flux. In the second part, flux is decreasing. So induced current wants to increase the flux. Whatever will be the cause, no, it will oppose it. It will just do the reverse. It will try to reverse it. If flux is decreasing, it will not try to decrease it more. It will try to increase it. If it is increasing, it will decrease. South polarity coming, it will try to repel south polarity. North polarity coming, it will try to repel north polarity. Whatever is the work is done, no, that time the cause is repelled. So here the cause is what? Decrement in magnetic flux. So it will try to increase flux. Now, if this is what all the magnetic field lines are going inside original magnetic field lines. Can you notice all these original magnetic field lines? These are pointing inwards. So if induced current, this is original magnetic field pointing inwards. If the induced magnetic field point inwards, then net magnetic field will be what? Original minus induced. If two vectors are exactly in opposite direction, making an angle of 180 degree, you subtract both the vectors, right? Both the vectors are subtracted. So if both the vectors get subtracted, your resultant magnetic field will decrease. Now here we do not want the magnetic field to decrease, because if magnetic field is decreased further, it will not oppose. Aim is to increase flux. Now, if induced magnetic field is pointing inwards and original magnetic field is pointing inwards and the induced magnetic field also points inwards. Now, what will happen to the net magnetic field? It will get added because both are in the same direction. Both of them will get added because both of them are in the same direction. Two forces, if two forces, 5 Newton and 10 Newton are pointing towards the right, what is the net force? You will say 15 Newton because they both will get added. Both vectors are in same direction. So by this, or even let's take example, had the original magnetic field been pointing outwards and the original induced magnetic field is also taken outwards, then also it will increase. Both these cases, magnetic fields are pointing in the same direction. So what happens to the net magnetic field? It will increase. So one option is this, other options are this. First option is either you can choose the magnetic field in the opposite direction to decrease field, or you can choose both the magnetic fields in the same direction to increase field. What should we choose out of 1 and 2 here in this case? Exactly, Razan. It should be, yes, somebody else is also answering. Imad, who was answering right now?
Ma'am, Asta.
Yes, Asta. Which one? First or second, Asta?
Second one.
Second one, definitely. Now, did you understand, Mariam? Why will it not be outwards? Why will it be inwards? Because when the original magnetic field is inwards and induced magnetic field is also inwards, there will be a net increment in the magnetic field. So, magnetic field will increase, and therefore, finally, the flux will increase. And that was all the purpose of induced current direction. So, this is clear, direction of magnetic field. All right. So if magnetic field has to point inwards, so keep your thumb inwards, keep your thumb in such a manner, right hand's thumb, in such a manner that your thumb points into the page. Keep it like this. Keep your thumb in the direction of induced current. So yes, Anushka, what is the direct curvature of your fingers?
Ma'am, into the page.
Thumb is into the page. Your thumb should point into the page. Why? Thumb should point in the direction of induced magnetic field. Here the induced magnetic field is inwards. So keep your thumb, Anushka, inwards. And tell me now the curvature of your fingers. How the fingers
Ma'am,
are
clockwise.
clockwise. Perfect. So your fingers are pointing clockwise. Like this. So induced current direction becomes clockwise. Yes, Asta, right. Now is it clear to all of you?
Yes, ma'am.
Yes.
Rayan, Mariam, Imad, to all of you, clear?
Yes, one of it.
Okay. Now note it down from the starting you were writing, no? This is a very important topic, Lenz law. You can only see theoretical questions are filled in up here. Just note it from here. Any doubts you have, still ask me. It's a very important topic. Mark this also as important in your notebook. That whenever you're doing EMI, Lenz law to revise karna hi hai. You have to revise Lenz law whenever you are studying or revising EMI. Lenz law from here and induction that we do. These are very core important topics.
Ma'am,
Yes, Asta.
from this topic, the laws can be asked and the direction related questions.
Direction related can be asked. That figure will also be given to you. Coil is there and a magnetic approaching bar magnet. That can be also given to you. Or simply that the question that we did, no, just right now, 2 coils, one entering, one leaving. Similar question is there in your NCRT as well. Random shaped coil is there and it is moving away or into the page, and you have to write all these things that we have discussed. No, that since it is going inward, so field lines will increase, flux will increase, induced EMF will try to decrease it, and all these points, whatever we have discussed, that you have to write it in your words. That will be a complete 2-marker or 3-marker answer. Like this, direction of induced EMF can be directly asked. Even direction can be asked, or simply statement of Lenz law can be asked. If only Lenz law is asked, from here till here, write it. Or you can explain it with the help of one example also by your choice. But if according to the marks, you have to answer.
Ma'am,
Yes, Anushka.
ma'am, today we have 2 hours class, right?
Yes. Yesterday I informed you all, no?
Yes.
And Liana, do tell me whenever it will become very late for you, because you have your exam tomorrow, I suppose. No? Tomorrow, it's tomorrow, no?
Yes, ma'am.
See, this is the explanation for the first part, no, that is written below. This is for the first coil, and this explanation is for the second coil. Done?
Yes, ma'am.
Almost done, the last.
Okay, one moment, just write it down.
Done one.
Okay, now one very small topic, let's discuss it. That is motional EMF. See, motional EMF is a very easy topic as compared to Lenz law and other topic. Lenz law is a topic that requires your concept, because if you do not understand Lenz law, direction of induced EMF cannot be given by any rule. Right hand thumb rule will fail, left hand thumb rule will fail, all the rules will fail if you're not able to understand the concept. Concept is simple. Oppose the cause. Flux is increasing, decrease it. Now, how to decrease it? That you have to arrange it by the methods that we have seen. Motional EMF is simple, a very simple topic. Derivation is also easy. See, motional EMF means what? Motional EMF. I have taken a U-shaped soft iron core. And on this iron core, no, I have kept a conductor. This is a conductor that I have kept. So let's say this conductor is some PQ. Let's name this PQ, RS Let's name this rectangle. But this is the conductor. Now what will happen? The conductor can slide or easily on this rail. It will act like a rail, these U-shaped soft iron cores. So PQ will move. Let's say with V velocity it is moving. So what will happen? If this moves closer, this area of this rectangle will become less. Then as it will move closer, again more close, then it will become lesser. So magnetic field lines will decrease. And if I shift the PQ, this conductor, towards the right side, then number of field lines will increase. So if this PQ conductor is sliding and hovering over this rail that I have drawn, this U-shaped rail, what will happen? Either increase or decrease in the magnetic field will be there. And so there will be the change in flux. As soon as there's a change in flux, what is the quantity that we get? Which quantity gets induced? EMF and current? Both of these, induced current is there and induced EMF is there. Now, since this EMF is continuously in motion, we call it as motional EMF. Motional EMF is nothing new topic. EMF you already know. All the properties of EMF you are aware of. Induced EMF was what? It was also not a new topic. Induced EMF was simply an EMF that was present because of change in magnetic flux. And when this magnetic field is constantly changing or the conductor is in motion, you say the EMF is simply motional EMF. Now, let's say L is the length of this conductor and X is the length of the loop inside, the length of the loop that is present inside or within the conductor, you can see. So magnetic flux is what? Derivation is very easy. Just pay 2 minutes attention here. You'll be able to understand this topic. Very easy, very small topic. Flux is what? BA. If flux is BA, tell me what will be the area of this rectangle, this inner rectangle. This loop, this U-shaped loop that I have taken, simply the coil, if I say it in easy words. What will be the area? Area for rectangle, I hope all of you know how to calculate this.
L into B.
L into B, but you don't have breadth here. Length is this L and breadth over here is X. So LX. Agreed? All of you?
Yes, ma'am.
Yes, ma'am.
All right. So area will be L into X. So put it here in term of flux. So flux becomes B into Lx. Now EMF is what? Minus d phi over dt. Put BLX over here. Minus, instead of phi, put it BLX. Now magnetic field is constant term because magnetic field lines are fixed in a region that is enclosed. That magnetic field lines are fixed, and length of the conductor is also finite. You have a specific length of conductor. This will not change, and number of magnetic field lines will also be the same in a region. But this X will change. This is variable because as the PQ will come closer towards then, X will decrease, and as it will move farther away, X will increase. So X is variable. It means B and L are constant. Whenever you're differentiating and you have a constant term, you write it out of the bracket. What is left? Dx over dt. We are taking the magnitude of EMF, so you can ignore the negative sign. Can anyone tell me what is dx over dt? Anybody from the class? Dx over dt. Change in the distance with respect to time or rate of change of displacement. Yes, class, what is dx over dt? Very easy term this is. Yes, Asta.
Velocity.
Velocity, perfectly. It is velocity. Dx over dt is velocity. So formula of motional EMF is what? BLV. This is the formula of motional EMF. This is BLV. Actually, we have written the negative sign was here. No, we have included the negative sign over here. We have taken it dx over dt. Why have we considered the negative sign within this velocity? The reason is that the reason for this is simple for dx over dt because velocity is in the direction where EMF is decreasing. So velocity is in the direction where EMF decreases. That's why we have taken this negative sign. But you can ignore this. So simply the formula of motional EMF is what? BLV. E is what? E is the motional EMF. B is what? Magnetic field. L is what? L is the length of conductor. V is the velocity of conductor. Now, BLV, just remember this. Motional EMF, immediately BLV should come to your mind. Now see, I is equal to E by R. We all know I is equal to E by R. So emotional EMF E is now what? BLV by R. This can also be used whenever required. Force is BIL. Remember force on a current carrying conductor, we did single conductor BIL. So from here, B, put the value of I, BLV by R. This is B, I and L. So this becomes B square L square V by R. That is the force. This formula can also be used. Power is force into velocity. So force is what? B square L square V by R into V. That becomes B square L square V square by R. So these extra three formulas can also be used. Clear? Easy? BLV? Understood or not?
Yes, ma'am, understood.
Yes, ma'am.
Okay, good. So note it down. Any questions you have to ask me. One numerical we'll do based on this as well. This is this topic is over. One question we'll do, this topic will be over, emotional EMF.
Ma'am, can I leave now?
Yes, Liana, you prepare for your exam. Best of luck.
Thank you, ma'am.
See, this question says an aircraft with a wingspan of 40 meter. Means the length over here that is given is 40. Speed is 1080 kilometers. This is your question from your NCRT. Kilometer per hour. So let's multiply it by 5 by 18 to get it in meter per second. So that becomes 5400 by 18. That is 300 meter per second. And magnetic field that is given to you is 1.75 into 10 to the power minus 5. So magnetic field is 1.5 into 10 to the power minus 5. Here this is the magnetic field 1.5. No, 1.75. 1.75. So this is 1.75 into 10 to the power minus 5. Now motional EMF that will be developed. This will be BLV, magnetic field multiplied by length multiplied by the velocity. So magnetic field will be what? 1.75 into 10 to the power minus 5. Length is 40 into 300. This much, just solve it, see whatever is the answer that you're getting, this will be your solution. Note it down quickly. This eddy current is not a part of your syllabus. How much the answer is coming? 0.21. Okay, Asta is getting 21 into 10 to the power minus 2. So note it down. Others also please cross check just once. Otherwise the answer will be Asta has solved it. It's 0.21. See, eddy currents are not in your syllabus. Let me just tell you them in brief. Eddy currents, see, whenever there's a change in magnetic flux, EMF is getting induced in it. Now, eddy currents are, eddies means what? Eddy currents is from the term eddies. Eddies means whirlpools in this form. This is known as a whirlpool, this shape. This is known as a whirlpool. So currents whose direction are like this, these are known as eddies. We call this as eddy. Again, I am repeating you, this has been deleted from the CBSE class 12 syllabus. So nobody is going to ask you questions from this. Let's just discuss this in brief. All right, so it is developed in sheets or blocks, thin sheets, very, very fine thin sheets that you have, or in the form of sheets whose edges are like this. From here, the eddy currents develop like this. They'll develop like this. Through the end, it will develop like this. This is known as eddy current. Fine. So there are certain applications in induction furnace, brakes, electromagnetic damping, speedometers. This eddy current is used. These are also known as Foucault current. So production and all you don't have to understand. Just remember this thing. Whenever on a sheet, currents are developed in the form of whirlpool. These are known as eddy current. There are losses also, hysteresis losses also you have energy loss. So there are certain mechanisms by which this is prevented, but mainly applications are there, and this is eddy current. Don't even note it down. If somebody wants to know, you can refer to the NCERT. In NCERT it is mentioned. So I hope you've written till here, or somebody else was writing.
No, ma'am. I've done writing till here.
Done? Okay, all of you just text me done in the chat room. All those who have done, then I'll stop the class. And now only induction is left. So next Saturday, we'll complete with induction. And in the next weekend, we'll start with alternating current as well. So now please prepare for electromagnetic induction, and your class duration will also now increase, because 1.5 hours class is very less. You just have 2 classes a week. So now at least it will be 2 hours class per week. Okay, then all those who have completed, you all can leave. In the next class, we'll start with induction. Please start preparing for EMI. You'll have a test of this complete lesson. All right. Thank you so much, class. Any doubts you have, you can ask.